Assalamu alaikum. Dear student, welcome back after the mid. We are going to start with the part 5 of the course, that is beyond Mendelism. So in this chapter we will discuss the concepts which we cannot address under the Mendel uh, laws, or which primarily deviate from the Mendel laws. Uh, so question: whether Mendel was wrong or right in his calculations. So we quote example jerky involuntary movement, that is basically related to Huntington disease, and that is this disease is prevailing because of the dominant defective copy of the gene. Now this disease appears in different age groups, and that depends on the repeats of CAG in the sequence of the DNA, and if there are 40 to 50 repeats of CAG in the DNA, then the Huntington gene, HTT gene, it would be active, and the disease will be seen in the adult on the onset of adult age. And in case of juvenile, the Huntington disease, it will not appear when the 40 to 50 repeats are there. So primarily if the gene is defected, then the disease should start from the early age. But now in this case the disease is the occurrence of the disease is dependent on the stage of the age, and that is dependent on the number of the repeats. Similarly, if the repeats are 60 CAG continuously, then the disease in the juvenile. So same same gene, but just the repetition is added, and now it appears in much earlier age. Now, when there are 27 to 35 CAG, then the individual does not catch the disease, or genetic defect is not there. So there are three different categories, you can say, when there are 27 to 35, or there are 40 to 50, and there are more than 60 repeats. So this is what we haven't seen in the Mendelian mechanism, or in the Mendelian laws. In that case, either phenotype appears or does not appear. But in this case, the phenotype appearance is dependent on the stage. So that is something deviation from the Mendel laws. So keeping in view, we can say Mendel was wrong, but that was not the case. Rather, it was deviation from the Mendel law. So the Huntington disease gene in human is present on the chromosome 4, and it's can be seen in the red, you can say red color in this photograph. Now, similarly, uh, another concept, dominance, complete dominance. We have seen the complete dominance. So do we need to revisit the dominance? So we see this example. You can see the highlighted part, the red flowers, A1 genotype, or A1 A2 genotype. So this is the dominant. Now when there is A2 or A1 A2, so it is the white flower. So flower color is either red or white. So we have to determine one of them is basically dominant, either red or white. But when we intercross these, so results are in A1, A2, and in the heterozygotes individual, we see the genotype is different. So if the A1 is completely dominant, then the heterozygote should be red. And if the A2 is completely dominant, then the heterozygote should be white. But here is the case is different. We can see the shades of the colors from red to the pink to the light pink, and then ultimately to the white. So this is the you can say the it's not completely following the dominance character here. And based on this, we derive some you can say basic things. Dominance phenotype of the heterozygotes is the same as that of the phenotype of the homozygotes, or homozygous zygotes dominant. Heterozygotes and homozygous dominant, basically they have the same phenotype. Now another case incomplete, which we have just seen this example, the phenotype of the heterozygotes is intermediate falls within the range between the phenotype of the two homozygotes. So this is what we have seen in the previous slide. And then the codominance, when the phenotype of the heterozygotes includes the phenotype of both homozygotes, meaning recessive as well as dominant. So that would be the case of the codominance. So these all three categories, basically they are deviation from the Mendel laws. Another thing is lethal genes. In this mice example, you can see the two heterozygotes mice with the Y gene and allele of capital Y and small y, they are intercrossed. And you see we have 1/2 yellow and 1/4 white, non-yellow. So non-yellow is basically homozygous recessive and the yellow is basically heterozygotes. But the homozygous dominant, that is completely missing. We cannot see that phenotype that should be red. And the absence of that phenotype is basically because of the lethal gene present. Because as the dominant in form of the dominance, when the both of the allele they are dominant, then it causes the death. That is the embryonic death, and we will never see this phenotype. This is here. This is another case, that is the basically case of the you can say deviation from the Mendel laws. Similar is case with the multiple alleles. You can see here the genotypes are MR, MR, then MR and M, MR and MD, then MM, M and MD, MD, MD. So you see the phenotype different. When MR allele is there, the phenotype is restricted. So it means MR is dominant over M or MD. And when MM is there, is mellowed. And when MM and MD are there, so again the phenotype is mellowed. So it means M is dominant over MD. And in third case, the MD, that is the dusky. And this you can see here in this example. So we are crossing, we are crossing the two heterozygotes individual, MR and MD. And the another one is the M and MD. And we get all four type of phenotypes. So rather, in typical Mendelian case, it should be two phenotypes. But in this case, you can see the four phenotypes. So this is the deviation from the Mendel laws. Similarly, multiple allele, this is another phenomenon which is not covered or which can't be addressed by the Mendel laws. Multiple alleles. In human blood type, everybody knows we have ABO blood type. And then it is more complicated with the RH factors. So here you can see, in this case, the phenotype of blood type A, okay, the genotype it would be I capital A, or I capital A, small I, and the antigen it would produced by this type of genotype, it would be capital A. But the antibody made by this type of genotype, it would be capital B. So just opposite. If the antigen is A, the antibody produced is B. Now, the B antibodies, when B antibodies are there and you cross, when you during the cross matching, you check it and you apply the B antibodies, and if the individual is A, then there would be no coagulation of the blood. And similarly, in the other example, you can see if it is the B, then the antibody, the blood type is B, and the antibody made is A. And when you use the antibodies B in the testing of the blood, there would be no coagulations. And same case with the AB type. And then AB type blood type, here you can see when only AB antibodies are there, it would be clear. Otherwise, it would be going to coagulate. And then the last one is the O. So O is basically, in case of O, there would be no coagulation. Either you use antibody A or B or AB or O, whatsoever is the antibody, you will get no coagulation. So that's why the O blood type is basically the universal donor. And in this case, you can see the AB. So AB type is basically universal recipient, because whatsoever the blood type you are donating, it will never coagulate. Thank you very much. So this part is completed. Please go through the relevant slide as well as the PPT as well as the other component of the PDF file, and prepare this lecture very well, because I'm going to give some exercises to be solved in practical part based on this lecture. Thank you very much.